Okay, good morning, everyone. I'm happy to be here, not just because I get to take off my mask, but also because the previous few talks have been very enlightening and interesting and actually have spared me some time to what I'm going to talk about today. I'll be talking about AI-driven decision-making for Industry 4.0. It's going to be a little bit more academic because I'm coming from IMEC Idea Lab, and I'm situating this talk was inspired by the last AI in Flanders vision, where the Flanders government has decided to pick a few focus points where they want Flanders to excel in HI. Obviously, that doesn't mean that we're only focusing on Flanders. We're happy to have collaboration between Belgium and all over the Benelux. So, how is AI in Flanders organized? Well, it's done by the so-called triple helix model. We have universities and strategic research centers as one helix, and those are in dialogue with both industry and the government, basically to strengthen each other and have use cases flow back and forth. I am today talking to you from the top part of the helix, from the knowledge center part, because I'm both involved at the University of Ghent and with IMEC. A few more words about IMEC. The academic part of IMEC is called ID Lab. It stands for Internet and Data Science Lab. We're located on two spots in Belgium, both in Ghent and Antwerp. We have over 350 internet experts. It sounds a bit old-fashioned to still talk about that, and data scientists. But the internet experts are still important because, as we've heard today about 5G or about communication on the work floor, communication protocols are still very important. Now, we're not just an academic partner, we're also having a lot of collaborations with industry. Coming from the engineering department, the link to industry is quite close, we find. And as I mentioned before, we have two locations in Belgium, and there we have over 40 professors active in industry-focused research. What you're seeing here is the location in Ghent, in Zwijnaarden, and we also have the Beacon in Antwerp. Now, these are just a few of our past collaborations with both local and global companies. You see here names from the creation industry, such as ArcelorMittal. We have, of course, pharmaceuticals with Pfizer. And then we have also collaborations with other AI service providers, such as RoboVision and ML6, or ML2Grow. What are a few of the products where you might already find ID Lab technology? Well, in artificial intelligence for computer-aided design, a simulation in the automotive industry, where we're able to drastically reduce the simulation times with automated ML. I will come back to this later in this presentation. We also have one of our medical applications was in combination with Barco, where we built a real-time analysis software to basically provide the physician with a device that can scan suspect molds and immediately report back on how likely they are to be an indicator of skin cancer. Further in the medical domain, we collaborated on an AI for sleep apnea, where we basically using on-person sensors tracked the occurrence of sleep apnea events in order to provide physicians with better input, better data to care for their patients. And finally, we're also involved in AI for recycling with a local collaboration with Recupel, where we created algorithms to help operators on the recycling line to basically highlight which object or what is coming down the line and how it should be treated. Should it go to the renewable, recyclable? Should it go to burnable and things like that? Now, step back a bit and go back to the Flanders AI program. Within the Flanders AI program, the government has identified four main research challenges. We have AI-driven data science. We have AI in the edge. You've already talked about edge before, as Serge mentioned in the main auditorium, and as Atlas Copco also mentioned before. We're talking about multi-agent collaborative AI and human-like AI. Basically, we're going to talk about all four of them today. We're going to touch on all four of them, but we're going to be mostly focusing on the AI-driven data science. Now, this is an Industry 4.0 conference, you can say. So how does this actually, what does it actually look like on the shop floor? And I'm going to go from left to right and highlight a few aspects where AI could be of importance. So AI-driven data science can help to make complex decisions. We're seeing here a picking robot, or a schematic picking robot that is asked to distinguish between different objects coming down the picking line. And this already brings up a first academic question, or an academic process that you need to go through when you're asking what is my application going to be about? Am I going to be distinguishing between different known objects? Let's say there's two different type of propellers coming down my line, and I need to basically distinguish between the two types. Then we're talking about a classification problem. Or are we going to look for objects that are out of spec, that haven't been characterized? Well, we know we have a characterization of what things should look like, and now pick out everything that doesn't perform up to spec. That would then be more of an unsupervised application where you don't have an entire description of all of the objects that will be passing down. You just know which ones you're interested in, and everything that doesn't belong to it, by definition, is going to have to be highlighted or picked out. From the previous presentation, Sergio was from Atlas Copco. I can't think of his name right now. He highlighted the need to have information travel on your shop floor, to have one operator spot something. He takes some time to mention this to another operator, so before it finally reaches a new decision point where an action can be taken to make a change in the pipeline. Now, if we're going to go to more and more automation, and we're having separate automated agents making decisions, we also need to find a way to have these communicate to each other. So we need to find a common language, or generate a new language for different decision-making entities to interact with each other. This is again where the communication expertise from the old internet experts in the ID Lab comes into play. We've also already heard mentioned about Edge a few times today, so I'll keep it brief. Why is it important that you are able to extract and process information at the edge? Well, because sometimes you can't send your data to the cloud. In a shop floor, you don't always have connectivity. Of course, we see with 5G promising to change all of that, that argument might start to, well, hold less weight. But even if you would be able to send your data back and forth, sometimes for a business security perspective, you want to keep your data in-house. And finally, from a safety perspective, if you're having an autonomous guided vehicle that is sharing space with operators, obviously you cannot tolerate any latency in interpreting if an operator is going to cross the path of an autonomous guided vehicle before an accident happens. From one of our previous applications in the automotive industry, where we employed cobots, we actually noticed that in order to have an accepted, or to have cobots be accepted on the work floor and not impede the efficiency of human operators too much, which can also happen, there was a need for operators to understand the intentions of the cobots that they're working with. Much like when we are going to cross the street, we try to make eye contact with the drivers on the street to make sure that we understand that I'm going to cross and you're going to stop for me. The same thing was observed in a cobot sense. Operators expressed feeling more comfortable working together with a collaborative robot if it had, and it sounds very, very, very silly, but if it had a facial expression. It was able to indicate to the operator, yes, I'm listening to you, and yes, I understood you. It even went as far as to incorporating little nods to make it that it becomes more accepted, and well, operators feel more safe. They feel understood and have visual cues that the cobot understands them as well. Another thing that we already heard about is digital twins earlier as well. Well, AI is helping you, of course, to basically funnel all the data that you have and turn it into actionable information. operators that have to, all of our IoT devices spit out a lot of readings and data. For an operator to have to interpret all of that data raw can lead to fatigue, information overload, and make it so that crucial science can get buried under basically irrelevant noise or not sensor readings that aren't important at that moment. AI can then help you to basically funnel the data, bring out which sensor readings are currently aberrant or out of bounds, and highlight that and bring it in a more usable, user-facing dashboard to make your operators actually process the data in an efficient way. In the context of digital twins, we also see that next to basically funneling the existing data or the measured data, we also have generated data pipelines that feed into that. And one example of a generated data pipeline would be a prediction for what is about to happen in the next few hours. Or something called soft sensing, where you basically, from observable indicators, you create a representation of the entire state of your system, even things that you cannot directly observe. And those kind of things can be used to alert an operator that even though everything looks fine right now, for example, in half an hour or in 3 days, we will have a shortage of this component, or this machine is going to create a bottleneck in the whole system. And for that, you need, again, the predictions in a user-friendly way. I will now talk about a few relevant applications and recent developments. I'm going to go progressively a bit more technical, but I'm going to start high level. So I already mentioned soft sensing and derived indicators. We basically collaborated with the European Union. Sorry, we were asked to find a more user-friendly way to monitor household energy consumption. You can put a little measurement device on each of your appliances in theory, but of course in practice that doesn't become workable very quickly. But you still need to, if you want to meet energy efficiency goals by 2030, provide users with insight in what are the main energy users. If you go beyond the household, think of a shop floor being run, also there for energy purchasing planning, it's important to know which of my machines are using the most energy, or even which are suddenly starting to use different amounts of energy than we expected. This is called non-intrusive energy. Wait, let me just go. It's about non-intrusive load monitoring, where you basically have one single measurement point on your main electricity line coming in the building, and you have one sensor there that basically captures all the variation during the day, weeks. And it's in this aggregated amount of information, it automatically detects events, things that are happening. An appliance that is turned on, and it recognizes that appliance in the last week, and highlights the specific moments in your time series where this happened. This is a way where AI can assist your exploration of your data, because it would not be feasible to do this kind of operation manually, where you have a whole week series of fluctuations, and you have to say, okay, this is my washing machine, these and these days, and this is my toaster. That wouldn't work. But if you're able to present an operator with, okay, we're seeing the same device popping up these and these and these times, spread throughout the week, please indicate which it is. There's a much more user-friendly way to get insight in your data. But in order to do that, you need to efficiently generate events, and basically from the whole jumble of information, all of the devices working together, automatically identify unique ones in the group. Why is this an especially difficult problem? Because there's fluctuation. We always have noise in our data. You can have even noise on the supply side. If your factory is equipped with solar panels, that is already going to lead to fluctuations in energy supply. So it makes it even more and more difficult to basically identify the energy usage in those contexts. This was a collaboration together with SMAPI. So again, initially it was focused on the households, but we're looking to extend this to industrial applications as well. And we see this often in our research that we start from one application field, be it industry or government, and we later generalize what we did and look for new markets to be able to provide services to new fields as well. A few shorter examples, and we'd like to briefly highlight acoustic monitoring for fault detection. Just from my personal experience in the last couple of months, I've seen a few applications or projects starting up that focus on, I don't know if it's by coincidence or if there's a real trend happening in the market where we see the same technology coming back again and again, or the same application coming back and again. And one of those is acoustic monitoring for fault detection. So why is this important? Why can it be interesting for industry? Because you do not need to install a potentially operation affecting sensor on each specific device. You could even go as far as to have an autonomous guided vehicle equipped with microphones that basically travels through your machine park and listens continuously to each machine and then highlights when something starts to change. This is typically an example of when cost sensitivity trade-off makes sense, because obviously installing a device on each machine would be much more sensitive, but it would come at a much higher cost. And depending on where you are in this curve, we see on the left you have the initial failure, all the way on the right you have the breakdown, and in between this curve you have a few different analysis techniques that are more or less sensitive. You would see that, for example, way in the beginning, ultrasound is one of the earliest ones that would be able to basically pick up something going wrong, but it's much more expensive than the acoustic monitoring, which we actually see on point 5, the audible noise. It comes much later in your failure path, but depending on your application, if you still have enough time to intervene and basically schedule maintenance, it can actually be the much more cost-effective solution. I also bring this up because we, as academics, also to make it clear that we're thinking about the practical application of what we're doing as well, and we know that there's such a thing as cost sensitivity trade-off. Another industry example is NIR spectroscopy, often used in online chemical process monitoring. What does it mean, NIR spectroscopy? It means near infrared monitoring for basically chemical reactions. It works by trying to observe the state of your mixture by looking at absorption of specific radiation, near infrared radiation. And if you couple this with insights into operating conditions, so if you monitor that, you're able to even distinguish between your machine starting to malfunction and your reaction going in the wrong way, or your reaction just reaching its desired result. For example, what does this typically look like? All of the different colors, each color corresponds to one NIR spectrum, and different colors basically indicate progression through time. This would mean that on the first little dip you see, talking about this is an absorption of a specific chemical component. It detects a specific chemistry in your mixture and is able to show you that your system is going from, if you're trying to cure a resin, for example, that you can real time visualize how far along in your process you are. This means that rather than using fixed batch process times, where we know that in the worst case this process takes 8 hours, depending on, for example, ambient temperature or things like that. If you are able to monitor each process individually, you're able to shorten your batch time a lot of the times, which means that with the same amount of equipment and operators, you can actually generate more revenue, you can increase your productivity. And this is a little example of how, by coupling both monitoring of your device and monitoring of your product, you're able to differentiate between your instrument going out of control on the left-hand side and your reaction going out of control on the right-hand side. If you would have only one of those two color-coded blocks, so to say, you wouldn't have the same insight in your system as you have by combining that kind of information, which is again bringing us to, in the future, or one of the next waves will be how to let automated decision agents communicate with each other. The next one I'd like to talk about is in the domain of data efficient AI, hybrid AI, we call it. We say that data is the new oil, but digging for oil is quite expensive. And even if you have a lot of data, you also have the concept of big scarce data, which means not all data is created equal. You might have lots of data, but only a very limited amounts of the data you're interested in. For example, typically you only have you have a lot of data on normal operating conditions. You hopefully have only limited data on failure mode, on machines in failure mode. The idea in hybrid AI is that you combine real-time sensor data together with potentially physical-chemical models and expert rules and human feedback. This allows you to basically create a hybrid model that is able to fill in the gaps, so to say, where you don't have enough data to generate a complete data-driven model, so a black box model, by inserting domain knowledge, such as an example would be if you know that if pressure goes up, if you increase the pressure, your temperature goes up, or the other way around. If that kind of knowledge could be inserted in your system, a priori, it would have to spend less time learning these kind of relationships. This is a very simple relationship. Experts are able to express much more complicated insights drawing from their experience. And if you find a way, and this is something that we specialize in, construct ways to have human experts express their insights, their years of experience. You're able to have your most experienced process engineers, for example, to unlock and leverage their experience and make it available to the whole plant. What this could look like is, it's again a lesson in the cost sensitivity trade-off. Typically, if you have more data, your accuracy of your model goes up. That obviously doesn't mean that we're going to always go to the extreme right of this graph because, well, data is expensive to collect and maintain. We can have diminishing returns of data, or we maybe don't even have the time to collect the data that we need. We need to be agile, we need to move quickly. So what we're probably going for is not something on the right, but we're looking for something more in the middle. We find a sweet spot between cost and performance. We make a kind of trade-off. Now, if you were able to move basically your whole response curve of your model accuracy to the left and up, this would be great, of course. We know that an automated system running without human supervision is often still going to perform less good than if you have a human in the loop to basically correct where the system is going out of bounds or the system is giving wrong results. Now, building in that human operator's knowledge in that system basically then means you push your entire operating curve to the left. So you can have the same accuracy with less data, which means you're having less investment risk, or you can go cheaper and faster by incorporating the expert knowledge. So you could, for example, for a desired accuracy, gain in data, but actually even create an entirely new set of sweet spots. So with hybrid AI, you can create even sweeter spots, basically, that's the point. One of the examples from a real application is where we used artificial intelligence for water leakage monitoring. We're able to drastically bring down the spatial resolution and the temporal resolution from 1 kilometer to 70 meters when a leak was detected, and to bring it down from the detection delay down from days to hours. And then finally, surrogate modeling. This is an older one, and I think it's been around for a while, and it's very exciting, and it still remains vastly relevant today. It does become it's the most technical of the three applications, but we'll get there. So I already talked a bit about labeled data. Your machine needing to distinguish between different parts coming down the operating line, or basically recognizing things that are in spec and out of spec. The in spec and out of spec, you would then sooner put it in unsupervised data, because you're not able to characterize all of the objects that you're going to see. Now, what does this mean? Basically that what you're going to observe, probably you're going to find different groups of clusters, groups of objects that are similar to each other, have similar relations to each other, but are very distinct from each other. What surrogated modeling is trying to do is, rather than, if you see on the left, to make one whole model for the entire domain, for everything you can encounter, it's going to make little submodels for each of the separate groups that you're interested in, or even within each of those groups, you can make further and further refinements. This basically is what surrogate modeling is all about, and it's a research group within ID Lab as well. We're operating there on the axis, or on the data landscape, where you have high value data, comes at high cost, but you only have a very limited amount of data. And surrogated modeling can then even be used to basically indicate to you where you should invest to collect more data. Now, what would this look like in the data modeling pipeline? We want to go from data to insights. Well, if we're able to help in the collection of the data, we're able to save on the cost of the expensive data. But of course, we need a way to have indicators in where we need to collect the data, what we need. So what we do is we build a first model, and we use that to basically explore our problem, generate first insights, and use those insights in that first model to drive new data collection operations. So rather than trying to characterize your entire problem space from the get-go, you start with the regions you're most interested in, generate hypotheses, test, and then go back to the most important regions. In this way, you can move faster and save on money. A few examples of collaborators there. This ties into the digital twin concept. I'm going to skip this because we already talked a lot about digital twins today. I'm just going to highlight two applications. We use it in basically the design of cyclones, where we had the issue that computer-aided design wasn't feasible anymore, because each simulation to design a cyclone and then test how it would perform in practice was taking way too many hours. We're talking about thousands of hours, which means that if you want to blindly explore, you're never going to get anywhere. So what we did is we basically used Sumo, surrogate modeling there, to drive our design, and to go from trying to characterize everything to a highly targeted set of objectives, and to start to use only, and to bring down the amount of simulations required down to 100. And if each simulation can take a couple of days, this means that this is already a significant investment, but at least it becomes feasible compared to if you would blindly optimize everything. What we then do is we present the engineers with a first set of suggested solutions. They're able to highlight or indicate which they find most interesting, and on that we start to iterate and generate new and new designs. We did a similar thing for the design of unmanned aerial vehicles for aerial photography, basically drones, where we again reduced the problem to a more maintainable set of solutions, and basically create a Pareto set of optimal designs. Pareto set means that each of those designs has a chance of being the best according to how you make the trade-off between, again, for example, cost and sensitivity. And my time is almost gone, so I'd like to conclude here and ask you to invite you to come and talk to me or my colleague. Contact me or my colleague Wouter Harik, both from UGent. I'll be around today during the lunch break and later as well. And I'd like to hear where you fit in the AI 4.0 landscape.
Thank you very much, Michael, for your expert talk. I also have a little present for you. Ja, iedereen heeft nu de tijd. We zijn pas om 2 uur hier terug met nog 2 expert talks van Bekaert de Slee en HoWest. En ondertussen kunt u van de catering genieten of een aantal exposanten bezoeken uiteraard. Tot straks hoor.